Okay. We still have homework 1, and it's still due on Friday. And there are lab sections that are meeting this week, which you probably know already. And there was supposed to be another announcement today, which was programming assignment 1 was going to go out today, but the person that was writing this programming assignment was just lazy and didn't finish it. It wasn't that I was lazy, it was just that there were tricky parts. So anyway, it should be out, I'm hoping tonight. So anyway, I'll put a post up when it's up. Today's plan is correctness and a little bit of runtime. Again, we're going to talk about loop invariants and how to prove things correct using loop invariants. But before we do, we're going to have a little warm-up. Here is the question. You remember tic-tac-toe? If you don't, it's an easy game. There's 2 players, the X player and the O player. The X player goes first. You put down a cross, an X or an O in one of these boxes, and then the next player gets to go and put down something in an unoccupied box, and you're looking to form 3 in a row. If you form 3 in a row, horizontally, vertically, or diagonally, you win. So we've interrupted a game of tic-tac-toe. And the first player, the X player, has already played, and the second player has already played. And the question is, who's going to win? So that's the question. And this is not like a philosophy class in which you could say things like, well, what do you mean by win? Or it's not a psychology class. And it could be that you would assume that maybe one of these people is not playing optimally, in which case you might assume that maybe they're not optimal players, but let's assume that they are optimal players and they're trying their best to win. Who has a win here? Everybody knows? Everybody knows? If you don't know, raise your hand. Otherwise, I'll call on you. Oh, really? You don't know? I'll give you 30 seconds. I'll give you 10 seconds. Okay. Who says first player win? Okay, great. Second player win. That would be interesting. And what's a good play for the first player? Any corner, right? I mean, any corner will do. And first player plays them. Okay. You might be asking yourself, what does this have to do with program correctness? This has a lot to do with program correctness. If we were talking about programs that were like 2 players that were playing against each other, and we were trying to come up with an algorithm for figuring out how to play one against the other. But we're not doing that. What this really was just a warm-up to get you thinking about something and trying to figure out like next move from previous move, and et cetera, et cetera. So there will be little warm-up things pretty much every lecture. And they may or may not be related to the lecture. This one, not so much. This is what we were doing last time. Last time we were looking at the code findMin, which was a code that I've now scrunched into 5 lines by cleverly putting multiple lines on one line. You can do that in C++ and C. See? You just string them along with semicolons and it all works out perfectly fine. Of course, it doesn't produce very readable code, but I understand that you know exactly what this code does already, so I didn't really worry about it, and it gives us more room for the proof. We got last time to the point where we had formalized the loop invariant that we were trying to prove about this code. You remember this code, right? This is the code that says, I'm going to pick up the smallest element at location B, I'll start, and then I'm going to try to walk my way through the rest of the array from B to B plus 1 to B plus 2 to B, all the way down to the end. And I will update the minimum if I run into something smaller. So it's basically collecting the minimum out of all of those, and then it returns the index of that minimum. That's the idea. And so our loop invariant is the formalization of this statement. It says, at any iteration I, for I in the range b plus 1 to n, so this notation here is a range. This is a range of integers, from b plus 1 to n sequentially. For any such I in that range, S is the minimum in the part of the array from location B up to location I minus 1. Okay? So it's a statement about all values of I, where I here is stand-in for that variable. And the other thing is that it's important to understand where this loop invariant is true. And the loop invariant is true right about here, maybe right there. So that's where the loop invariant holds. Loop. Something around there. Okay, any questions about the setup? Because if you don't get this, then what I'm going to write is going to be, maybe it still will be, but it will be more understandable. No? Okay. How do we prove this loop invariant? We had several candidates for proving loop invariants, but this is a loop invariant that's trying to show that something is true as we go through an iterative process that's going and increasing I by 1 each time. And the correctness of the statement at iteration I depends on it being correct at statement I minus 1. And so the key trick, or the key technique for handling situations where you want to prove something is true for all values of some variable, given that you can show that you can get from one step to the next correctly, is induction, right? That's the whole deal with induction. So we're going to do proof by induction. And what are we going to do our induction on? By induction on something. Some parameter. No? What parameter would you like? I'll tell you, remember, this is induction that's trying to capture the success that we're making as we progress through the loop step by step. So it's almost like the inductive proof is being handed to you in the code. It's basically saying, as I progress in this particular way, by following this particular loop, I am making more and more progress towards being ultimately correct at all iterations. That's the hope. That's what we're trying to prove. So what would I do induction on? Okay, well, you could invent your own variable. You could invent a variable called k, and you could do an induction on k. But what would k be related to? No? Maybe this could be a trick question, but it's not. What's the thing that this is going to be induction on? What's the only thing that's moving here? I. I mean, we could invent a variable k which counts the number of times I'm going through this loop. We could say k is the number of iterations of the loop, and k starts off as being 0. But then when we want to index things in our proof, we would have to use something like, k plus b everywhere instead of I, which is what we really want. So let's do induction on I. And if we do induction, the first thing that we have to do is what? What's the first thing in a proof? Here. Well, you're exactly right, except that I didn't say it exactly the way I wanted to say it. What's the first thing we have to do in this proof? It's a little bit different. We already done something in this proof. We've decided how we're going to do induction. But even before that, we had to do something which is something that's important, which is to believe that what you're trying to prove is true.
Assume your assumption?
No, not assume anything, just believe it. Do you really believe that this is true? I mean, if you don't believe it before you start writing down a proof, then you're like walking around in a minefield with a blindfold on. I mean, you don't know where you're going. You got to believe it, and you got to believe for some reason it's true before you can prove it.
So that's the first step. But we have already yeah.
Isn't the thing that makes proofs useful, though, is that you don't always know whether something's true or not? Like solving problems that you can't really understand fully.
That's true, but you have to believe something before you can prove it. I mean, you have to, I mean, you can maybe not commit. You can say, I don't know if this is really true until I write out this proof. But the fact that you're writing out a proof means that somehow in your head you've decided that this is worthy of being proved, that it's something that could be explained. Oh yeah, this reminds me of something else. This is 221. This is no longer 121. So as you work your way up the theoretical computer science chain, your proofs will get more and more wordy and less formula-y. It's not really great grammar, but it means that there are going to be less and less simple formulas that you write down as a proof and more things where you have to write a sentence that says something. That's what this proof is like. It's not just going to be a bunch of symbols strung together in a formula. It will be argument. And some people are very uncomfortable about that because they want to work from the, the bare metal, like way down at the bottom. What are the axioms on which we build this proof? What are the things that are like in geometry? What can we take to be true? And we're above that. We're like sitting on the swamp a bit. It's a little squishy, a little uncertain, but it's a proof for convincing yourself and convincing a reader that something is true. So that proof has to take in mind who your audience is, and it has to be as careful as you can be so that when you get done with it, you actually believe that the code is going to work in this case. I know that's uncomfortable. I wish it was a formula. I wish it was as simple as that, but it's not. They're all different. Well, I don't wish that because then I'd be out of a job. So, okay, so let's, but you were absolutely right. At this point in the statement of this, we have the theorem, we have the loop invariant that we want to prove. We know what we're doing by proof by induction. We believe that it's true because we have this long talk about it. So now let's just prove it. So we've got a base case that we want to look at. What's the base case? This is going to be really slow and tedious if I don't get crowd participation because I am a patient man.
This holds for B plus 1.
You want to start at I plus 1 or B plus 1?
This holds for
Yeah. That'll work. Base case, I equals B plus 1. So what's set at before the first iteration of the for loop? Before anything actually happens, I is set to B plus 1. So this really is, in other words, before the loop starts. Before the loop executes. So it hasn't even executed once. And we want to check to make sure that this statement, our loop invariant, is true when I is equal to B plus 1. So we read this, and when I is equal to B plus 1, it's saying that AR is the minimum of AB through I minus 1, which in this case is just B, so it's a range which has just got one thing in it. And what do we know? We know at the beginning, we know that this is B at the beginning. So remember, this is all base case stuff. That's B. There's only one thing in this minimum, AB, and we're saying that AB is the minimum in AB at the start of iteration B plus 1. Do you believe it? It says AB, the string AB, because R is equal to B, is the minimum in the range A, B through I minus 1, but I is B plus 1, so I minus 1 is B, so it's the range A from B to B. People are not happy. let me explain something. This notation right here, the little dots, means b, b plus 1, b plus 2, b plus 3, all the way up till I minus 1. But I minus 1 is just b. So this is just b. This also, the same little dots here, are the same deal. This is supposed to hold for I equals b plus 1 all the way up to n. So we're starting off with the smallest value we care about, which is b plus 1. Are you happy? Good. I'm happy too. Let's go. Now what do we do? Got a base case, inductive hypothesis. Inductive hypothesis is essentially the statement that we're trying to prove for the values. We assume that it's true for the values up to a certain point, and we want to prove that it's true for the next step. Sometimes you only have to assume it for the previous step, and you get the next step. That's what we could do here, but we might as well just assume it for everything. So we'll assume, we won't. We'll just assume at the start. Oh, by the way, if you're frantically writing this down and you're not paying attention, that's not good. And to alleviate that situation, I've written the proof and put it on the website, and it's on the same place you go to for the lecture notes, but it's called proof. So if you don't want to write anything, don't. If you want to go enjoy the sunshine, go ahead. But then we're going to get done with this proof, and then we're going to go to do stuff that's different. So you'll have to come back. Okay, assume that at the start of, oh yeah, that's the other thing. I'm going to abbreviate iteration. Don't get confused. This is iteration. Iteration I, that S is identically AR, I'm just writing down the statement, and is the min of, in this array, A, B through I minus 1. That's our inductive hypothesis. We're going to take an inductive step, and we're going to try to show that it's true. So there's our inductive hypothesis. We're going to try to show that it's true for the next value of I, so I plus 1. Okay, so that means we're currently operating on iteration I. Okay, we've just entered iteration I, and we want to show that it's true after iteration I, or in other words, at the beginning of iteration I plus 1. That's our inductive step. Okay. So what happens during iteration I? During iteration I, what do? We compare. Can you read this, by the way? Anybody not able? Anybody unhappy? We compare S, and what is S? Well, by the inductive hypothesis, S is the minimum. It's AR, which is the minimum of it's the minimum of A, B, I minus 1. Those are dots. This is by the inductive hypothesis. So it's comparing this X, this S, it's comparing this S to A sub I, and it does something if A sub I is smaller. So how's this going to work? I mean, here we have code, and it's doing two different things. If A sub I is smaller, it does something. If A sub I is smaller, it does something. If A sub I is not smaller, it doesn't do anything. It just goes to the next iteration. So we somehow have to capture the fact that there's two possibilities within this proof. We have to be able to say something about either one of those possibilities. So let's talk about the first one and say, well, actually, I'm going to just talk about the first one. If AI is small, phi is less than s, then we replace r. Oh, that's cool. Oh, that's even better. Come back. Okay. We replace, what are we replacing? Oh yeah, we replace r with I and s with a sub I. And at that point, we know that even if we didn't do anything, if it wasn't the case that a sub I is less than s, we can say the following. Thus, at the end of this iteration, AR is equal to, it's the minimum of two things. It's the minimum of the thing that was a sub r before the comparison, which was the minimum of b through I minus 1, and AI. So it's the minimum of two things, one of which is the minimum. That's the thing that we got from the induction hypothesis. That's what a sub r was. And we took that and got the minimum of that with AI, the next value in the array. And that minimum, the minimum of those two things, is just the minimum of the whole thing. And so we're getting that for I plus 1 at the start of the next, and then the loop returns to the beginning. And then we go to the start again. Then we go to the start of the loop. Cool. Of loop I plus 1. And the invariant holds. We go up, we increment I, we're now in the loop I plus 1, and we know that the thing that's in a sub r, is also in S, is the string that's the minimum among all of the elements from B up until the new I minus 1, which is the old I. There you go, okay? Yeah.
So what's your proof was explaining what's going on in your code?
My proof explained what was going on in my code, but it pointed certain things out that had to be true from the past iteration in order for me to make the claim that I'm making about the next iteration. Like this right here is from the inductive hypothesis. It's not from the code. It's just a fact that I happen to know because I believe the inductive hypothesis from the previous step. And so, yeah, but I had to write down what was going on in the code to a certain extent. I mean, I could have done more of that, but I didn't do as much as I could have done. But I had to do some of it in order to explain what the operations are that were manipulating the data that I was working on. So that manipulation is encapsulated just in this statement here. It replaces it only when I is less than S, which is essentially saying that that min operation is what's happening. This one right here. I'm taking the min of what was there, which is AR, and AI. And I'm stashing that into the new version of AI.
So is the key here, like bringing back your base case so that it holds true for like, continuous iteration?
No, the key is bringing back the previous, well, in this case, it's the previous step. It's the previous, it's not the base case. I mean, it will eventually trickle. It will eventually trickle all the way back to the base case.
Right.
But it's just one step back here. Yeah, it does sound, I mean, I see a lot of proofs that just write down what the code does. But there has to be some part of it where you're using the inductive hypothesis to say it's going to work in the next step because it worked before. Otherwise, you're maybe not capturing the right inductive invariant. Yep.
So I'm just a little confused. In your induction step, when you said A of R is now the minimum of the previous minimum with the current one is now equal to min of A from B to I. So are you saying that you're essentially shifting one forward?
Oh, no. What I'm saying is that min is a very special operator.
Okay.
If you take successive mins of things, a min of this and a min of that and a min of that, and you take the min of all of those things, what you'll get is the min of everything.
Yeah.
That's just an arithmetic fact about min. So think of it as being, if you have the min of something here, and you have the min of something here, or anything here, and you take the min of all of it, you're going to get the min of all of it. Let me just give you the, so it's like a, do you guys have this in Racket? Did you have flattened? Did you ever do flat? No? What are they teaching you in that class? You flat out the parentheses. It's sort of like that. Like you're taking a list of lists and you flatten it out and make it be one list instead. Okay, never mind. Any other questions about this? Yep.
So the key here is that you have to link the next step back to the previous step, which involves your induction hypothesis and why it would work for all previous steps. You link that to the next step.
That's right.
Okay.
That's exactly the key.
So to, I guess, just confirm, the crucial step or line is the second last one, that includes the inductive part of our proof. It brings it all together.
I'd like to think of all of those lines as being important. But you're absolutely right in that that's the culmination of all of the previous lines. We had to be able to say that in the previous line, we had to say that A sub R is this min in order to be able to say that when I take the comparison between AI and S, which is AR, that when it's smaller, then it will do this min of these mins. So I had to use that fact and that's the use of the inductive hypothesis. So yeah, I mean the important part in this proof is really the use of the inductive hypothesis. Yep.
So could you go over again why within A in the bracket it's B dot dot I minus 1? Could you just explain that part?
You mean here?
On the loop variant, like put an arrow towards it.
Oh, way up there.
Yeah.
Well, think about the initial base case. We decided the initial base case was B plus 1. Okay. Well, that agrees with the index I at that iteration of the loop. So the first iteration of the loop happens with I equal to B plus 1. So what I did here was I took that variable I and I used it in place of an inductive variable. I used it as the inductive variable. And so now I needed to tailor my statement, my claim about the loop invariant. I had to tailor that to my choice of variable. I chose this variable I, which matches the code nicely, but it means I have to be careful about what I'm claiming. And when you enter the loop, when I is equal to B plus 1, when you enter it for the first time, you know that the only thing that you know is that the minimum that you have, which is A of B, is only known to be the minimum of A of B. You haven't looked at anything else. So this has to be an I minus 1. It can't be I, for example. Now, what I thought you were going to ask is, what about this N? because the loop never gets to n. I never gets to n. Why do I have n in there? That's what I thought you were going to ask. But you didn't ask that, so too bad. No. Are you curious about why that's n? Yeah, because I'm claiming that this loop invariant is true for a value of I that isn't actually executed within this loop. I equals n is not a value for which the loop executes. However, it is a value that's achieved by I when? At the end of I plus 1, at the end, yeah, I plus plus, on the last iteration of the loop, when it comes back up, it increments I, and then it does the test. So my loop invariant holds at the end of the iteration where I is equal to n minus 1, it holds at that iteration, and that implies that it's true at the beginning of iteration plus plus I, which is n, but immediately the code gives up. It says, I is not less than size, it falls out. Why would I want to prove the invariant all the way up to n? Why would I want to make that claim? It's kind of confusing, because it's true that the only time that I achieves that is right before this comparison is done, right there, and it falls out of the loop. That's the only time that I is that big. Why would I want to do that? Yeah. So that after the comparison fails, the R value that I return is where R is the index of the smallest string from index B all the way up until the end of the array, which is index n minus 1. So this, the fact that I went to n here, has nothing to do with the loop invariant. What it has to do with is the usefulness of the loop invariant in proving that the code is correct. If I didn't go up to n, I'd stopped early and said, I don't care about that last bit. I don't care about the last iteration being correct. Then I wouldn't be able to prove correctness. But with this thing at n, it's okay. I can do it. Yep.
Since like when I equals n, the loop doesn't do anything, can we like adjust the indexing of the loop invariant so that it becomes like AR is the minimum in like adjust the indexing at the end of the iteration I, where I is like from B plus one to n minus 1?
Yes, you could move the location of where the invariant holds, which is what I guess you're saying. Yeah, you could say, I want to prove an invariant that happens at the end of the loop, the bottom of the loop. But for this loop, you have to understand that the bottom of the loop is the same as the top of the loop. Nothing happens in between the bottom and the top, except that I gets incremented. So your suggestion is exactly what I'm doing. It's just that I'm saying the increment happens. And in fact, if this was in C, if this was good old C, not C++, where you can't declare ints inside of for loops, you have to declare them outside of for loops, then at the end of this loop, actually I would have the value n. It wouldn't have the value n minus 1, it would have the value n, because it would be incremented and the test would be performed, and then it would fail and fall out of the loop. So I kind of like it this way, because I can't tell you the story about C versus C++. C++ just, it releases I. I is no longer in scope. It's no longer a valid variable to use after it's out of its for loop in this case.
So
yes?
should we include it or not?
Should you include what?
N.
You should do it exactly like this. Now, you can do it whatever you want, but remember what you're going to have to do with this. You have to prove that the algorithm is correct. And this makes it easy. This is saying, when this fails, I is n. When this loop terminates, when it's not failed, when this loop terminates, I is n. And then you read that statement, AR is the minimum in B, A, B through n minus 1, and that's exactly what you want. You exactly want that. You want it to be the minimum from all of from all of those indices. And that's what this code does. I mean, you couldn't, you know, it doesn't forget about the last element, for example. Okay, great. Here's the summary of how to do loop invariant proofs. First of all, choose an induction variable. Well, first of all, believe that the thing that you're trying to prove is true. Secondly, think about induction and where you want to put the loop invariant. And then figure out what inductive variable you want. And usually the inductive variable is the number of times you perform the loop, the number of times you've executed the loop. Now, you could use, like I did, the index, if the index is behaving nicely, being incremented by 1 each time, for example. You could use the loop index if it's nice. If it's, how do I say nice? It behaves nicely. It's being incremented by 1. If it's capturing a number of iterations. It's, you know, that's exactly what our I was. It's just that I happened to start at b plus 1 as opposed to being starting at 0, something like that. But it was a lot easier proof to read if I used I as the loop invariant. As the induction variable. Okay, then you prove a base case. The base case for what, you know, I don't really see a point. Okay, I should be honest here. There are many authors that write books in which they spend a lot of time explaining why you should be putting loop invariants at the beginning of a loop or putting them at the end of a loop or putting them where. I don't really subscribe to any rule about that. You can put your loop invariant where you like, but it seems to be pretty easy to put it at the beginning because it's the same as putting it at the end. The only thing that's different is that you might have a +1, -1 issue. So, okay. So the base case, you prove the invariant is true before the loop starts, or if you wanted to put it at the end of the first loop, you'd prove it after the first iteration of the loop. Like if you were in a do-while loop, do something, while something. Yeah.
I read one book where they kind of made the argument, and they were saying like it's best if it's true for his like, or it's like it's the invariant is false for as short a time as possible. But I guess it doesn't really matter if you're only checking in places where it's gonna work out, right?
Oh, that's what their claim was?
Yeah,
they wanted to make that
like,
it's short?
It's like if you do it at the top, there'll be like 2 lines where it's not true. So like it's better to put it here.
Wow. See, those things annoy me so much that I don't even read them. That's bad. I should read them. But that makes no sense. I mean, you want the invariant to hold at a particular point in the code, and the reason why you might want it to hold for multiple lines of code is just because you're trying to make claims about what the operations of those lines of code are doing to this invariant. So it might be less confusing to say, you know, I have to argue that there's a change in what's true as I march my way through these operations that are being executed, but I don't see any reason why one would want that. Then again, I have not written a textbook, so how could I be an authority? But I've written a lot of proofs by induction, that's for sure. Okay, the inductive hypothesis. You want to assume the invariant holds just before the beginning of some iteration, and then take the inductive step, prove that it holds for the next iteration, and then the final part is this extra bit we were just talking about, which is you really only want this loop invariant to prove the program is correct. So after you've got the loop invariant proof, you need a little bit of extra in order to use the loop invariant to show that the program is correct. And that's what we just did when we looked at looking at I equals n.
Sorry, I have a question.
Yeah.
How will we explicitly show that the extra bit works? So like in the previous example, how will we explicitly say that this inductive step holds true to that? Like how do we explicitly say that?
You say so we assume the inductive hypothesis for all values of I up until some point.
Yeah.
And we would put a condition here that says as long as I is less than or equal to n minus 1, we can do the inductive step.
Did we mention that at the end of our proof?
Well, you know, actually, it's a good point. I should probably have mentioned it right here. As long as I is less than or equal to n minus 1, we can perform the inductive step. Because what happens if I is n and we try to perform this claim? Nothing happens. If I is n, it will not execute any of the code that's in between. It will just fall out. So all this argument about what happens during iteration I assumes that I is small enough that these things actually happen, which means I is less than. Right. So it's a great question. Thank you. Any other great questions, or even not great questions? Or all questions are good. Okay, this is the big thing, though. See the bottom down here? This thing? Let me see if I can move it. No, I can't. This proving correctness is only one benefit of loop invariance. I'm not teaching you about loop invariance because I expect that you're going to go and look at your code and prove it to yourself that it actually is doing what you think it's doing. That's not the point. The point is to think about the code using this idea of progress through a loop. There's some sort of invariant or some sort of property that you're trying to preserve as you go through this loop. And that's a way of thinking about programming. It's a way of building correct code, is to understand when you're going through a loop what it is you're trying to maintain, what property is it that you're trying to build into the code. And making sure that you're thinking about that while you're doing your coding means that you'll produce, hopefully, more correct code. Or at least you'll understand when you go wrong. Plus, it's a great thing to put into comments. If somebody doesn't know what your code is doing and they look at a comment that says, I'm trying to maintain this property, then they've got it. They are understanding what's going on. Okay, so that's the big pitch for why we're interested in it. Also, we like to prove things are correct, but that's here. Okay. All right, great. Now, this is interesting because this is another piece of code, but another piece of code that's using the find min operation that we just defined. Okay? So it's doing a find min from an index I that's starting off at 0 and it's marching its way through this array. What is this code doing? Remember, find min is the thing that picks up the minimum from index I until the end of the array. It picks up the minimum thing from that range of values, grabs it, and gives you back the index. Oh, and by the way, swap means swap. It's taking the array location, the thing in array location I and the thing in the array location min, and it's swapping them. Before you answer this question, let me ask you a question. How would you implement swap? I have to tell you, this is one place where it was a lot uglier in C. You could do it, but it was a little uglier. This is beautiful. How would you implement swap? Yeah.
By using a temporary variable.
By using a temporary variable, good. But this is a call to a function swap, right? So if you did something like temp equals AI, a sub I equals a min, and a sub min equals temp, which is the way you normally do a swap. If you did that in a function called swap, what would happen?
You're out of the function, they're still in position.
When you return from that function, they would not have been changed. Unless you pass by reference. Very good. That's what everybody was thinking in their heads. Sorry. Pass by reference. If you pass these values by reference, then any changes that are made inside of the swap routine are reflected in the caller, which is this code. And so that's what's doing the swap. So it's actually pretty straightforward to do. Yeah.
Great. So just as a refresher, that and sign and the top, that means pass by reference, right?
That. Yep.
Yes. Okay.
which is, for example, why I don't have to return the vector. This is a void function. It doesn't return anything. Why? Because it's doing something to the vector A that's going to be reflected in the person that called. Okay, so now that you know what this does, what does this do? I don't care.
Sort ascending.
Sorts. It sorts in ascending order. Very nice. Or non-decreasing order. Yeah. It's a sort. It's called selection sort. And what do you think the loop invariant is for this? I mean, it's got a loop. How did you know that it sorts? I mean, what's the property that's being preserved here in this sort? Come on. Yeah. I'm sorry? No, that's not an invariant. I need a statement. I need an invariant that says something about something. Yeah?
All the elements that have been checked, it's in size order.
Okay, great. A0 through I is sorted. Everybody happy with that? That's a good invariant? Yeah.
The other half is unsorted.
Well, it could be sorted. We don't know that. But what do we know about this group here? Not only do we know that it's sorted, but it's important for the correctness of this code that there's another property of the things that are in this A0 through AI. There's a second thing that's true, which is important. Yeah?
So all of the elements from 0 to I are smaller than the rest.
All of the elements in this array are smaller than the ones that remain. And smaller than a I plus 1 through n minus 1. And then there's another nitpicky thing. And the set of strings in A hasn't changed. That's why we're doing the swap. And the swap is there to preserve the contents of the array A, not in the same order, but to preserve the set of elements that are in the array A. So these are all important things for the invariant, because when you're trying to prove this invariant, you need all of these things to be true in order to take the inductive step. You need all three of them to take the inductive step. Yep.
Would it be smaller or equal?
Oh, yeah. Okay? Watch this. No. I think I have time for lots of questions. Anybody have any question about this? Like, for example, how we prove it? This one is easy. The hard thing about this one is the statement of the invariant. Once you have the statement of the invariant, figuring out what find-min does, we already did that. Performing the swap, we know when we're supposed to perform the swap. We're supposed to perform the swap because we're trying to pull the minimum thing out of the stuff that remains, putting it in the front. And so this actually is a pretty simple proof. What's the runtime? What's the runtime of find-min? Big O of n squared if we had the comparison, but I'm going to force you to think of the comparison as being constant time, because that's my prerogative. Though you're absolutely right, it's possible that that's not a constant time. So we're going to say this is order n with a constant time comparison. And if that's the case, we're executing this loop n times, big O of n each time, plus a constant. Runtime is big O of n squared. Is this tight? I'll let you think about it. We have to go. I'll see you on Friday.